Hi, this is my presentation of detection of scintillation events using supervised and unsupervised machine learning. I'm Michael Whitney from Science and Technology in Oslo, and this presentation and article stems from it's made with the help of ESA, Tech, the people who were Monitor, Paulo Costa, and Richard Swin. So first I'd like to provide some background into what scintillation is. Scintillation is a term from the space weather field. Space weather relates to the upper atmosphere and how it interacts with the solar wind. As the sun doesn't simply impact the earth by simply sunlight, it also impacts this by sending plasma through the solar wind, which interact with the earth's magnetic field. And these can cause a storm activity in the space weather. And these can cause numerous things. Most known is the aurora, which occurs in the high latitudes. However, these can also cause disturbances to GNSS, power outages. They can cause radiation damage to pilots and astronauts, to name a few, as this has a wide impact in many industries. One type of disturbance is called scintillation, and this is a rapid modification of radio waves when the signal passes through ionized plasma. Sometimes during storm activity, scintillation increases greatly and can cause high inaccuracy or loss of log. So when a satellite sends a signal through the GNSS receiver on the boat, when it passes through the ionosphere, scintillation might occur, which can give it a high inaccuracy. So the boat messages might be sent to the side, or it can just completely get a loss of luck, which means it doesn't know where it is at all. So then we would like to go through a data analysis part. We had about 9 months of data, which was observables from the Kiruna station in Sweden. And this was about 45.6 million data points, just to give an estimate of how much data this was, because this was 24/7 from numerous satellites in the Galileo satellite system. And the data was labeled based on phase scintillation index, applying a majority vote over sliding window of 5 minutes. And this was performed, both the data and the labeling process was done by the AIM-GNSS team. To put it plainly, the labels look for high sustained scintillation values. So if it would label an event if it has high sustained values, and that was likely an event that would cause high inaccuracies or loss of log. And then you have the non-events, which would be the calm, quiet times. So, and we saw that the scintillation event is only about 1.5% of the data. We then like to look at the features that will be the inputs for a machine learning algorithm. So the first two we looked at was the day of the year and what time of day the measurements took place. So at the left there you can see day of the year, and the top one is the event. So it's the data that are events, which means they have a high phase scintillation and likely cause the high inaccuracies or loss of log. And then you have the non-event, which is the calm data in the more calmer periods of time. So what we can see here at the bottom here in the non-event, for day of the year, there's a smooth, nothing particular pattern there that comes up, but we might see some seasonal change here at the event, that there might be some days of the year where phase scintillation might occur more often than other times of year. But I don't think we have enough data with 9 months. We likely have to look at more years to determine that. But that would be an interesting thing to look at. On the right here we have what time of day the data occurred. So you can see that on the x-axis. So you can see here immediately that between about 10 o'clock and 4 o'clock there's a big spike in events occurring at this point, while the non-events are just calm all through the day. So this was likely lead that phase scintillations occur more at night. So this is the two more features that we looked at. This is the azimuth and the elevation angle. The elevation is a measure of where the satellite is compared to the receiver, where the satellite is at the horizon, it would be 0 degrees, and straight above the receiver would be 90 degrees. So, and azimuth is also a measure of where the satellite is compared to the receiver, but it is where it is in the cardinal directions, where north is 0 degrees. Here we see that the azimuth, we didn't find any particular pattern here, as it was mostly very similar to each other. But in the elevation, we found that there's less events compared to non-events at higher elevation, and there's more events than non-events at low elevation. So we've explained that to be that at lower elevation, the signal has to cut through more atmosphere, and it can get more disturbances, can encounter more scintillation in these levels. So we think that this makes sense. So here we also have taken a look at the signal to noise ratio of the signal L1 and L5, and since this GNSS receiver has access to receiving 2 frequencies, we looked at the signal to noise ratio to see how strong the signal was compared to the noise background, and we didn't find any particular pattern here either. So here we have what we call the phase geometry free, and this is a feature where you have the 2 frequencies traveling to the receiver, and these 2 frequencies will move at different times, as they are essentially a little bit different. And here we have just subtracted the one frequency length minus the other, and we can see that since the ionosphere is a dispersive medium, that the speed which the signal travels through the ionosphere depends on the frequency. We can see some changes in this. We can see that in the vents, we see that there's a slight tilt to the right, so there's less difference between the 2 signals. And we also see that there are 2 peaks on the vents here, and we don't have a particular good reason why this occurs. So here we have 2 very interesting features. The one on the right is the phase scintillations themselves. This is what we have labeled the data on, and we can see that the labeling algorithm have taken these top values here and labeled them as high phase scintillation values here at the side here, and these are the non-events. You can see that the non-event stays at the very low values, while the phase scintillations is very scattered. On the left here we have what we call RODI, which is a measure of how fluctuating the space weather is at the given time, and you can see that there's a big correlation, very similar to the phase scintillation themselves, and they have very similar shape, and this we'll come back to. So before we went through training the machine learning models, we did a feature selection for the models, as we did not include all of the features. We chose the elevation, the azimuth, the signal to noise ratio of both the signals. We did the phase geometry free, and we did the ROTI. We did not do the time of day or the day of the year, as time dependence is not desired at the GNSS receiver, as it can move to different time zones. So we wanted for now just remove the time independence and see how it performs with this. And also we didn't include the phase scintillation, as this was used for labeling, so we decided not to include it. So before we go into the models we'll use, we want to go through the metrics in order to understand what makes a good model and what makes a bad model. There's 4 different cases that can occur. There's when there is an event and the model predicts an event, so it's correct. And it's when it predicts an event but there's not an event, so a false positive. There is when it predicts a negative but it's actually positive, which is a false negative, and of course when it actually is a negative and it predicts it, so this is a true negative. So these are the 4 cases, and out of these 4 cases we devise our score functions. So the simplest one is the accuracy, which is just the number of true positives and true negatives, so the number of things it got right divided by the number of data points in total. But the problem with that is that as this is a very imbalanced data set where events is just 1% of the data, the other 99% gets a very imbalanced weight to it. So the models can be learned to guess only non-events and get a pretty good accuracy score from that. So that's not a particularly good score functions for this case. So we'll focus more on recall and precision. Recall is how many events were detected out of number of possible, while precision is how many false alarms are there as you use the model. And we argue in this case that recall is more important than precision, but both are important in themselves, as recall is likely you want to detect as many events as possible, but false alarms is not that dangerous in this case. So in this paper we have used supervised learning methods, and we used four of them in this case. So there's the care nearest neighbor, there's the decision tree, and the random forest, and AdaBoost. So before we move on to explaining what they are and how they perform, we would like to introduce two terms from the machine learning world, which is underfitting and overfitting. Underfitting is when you have a very simple model that it can't properly model the pattern. So when you have something too simple for the pattern that is too complex, the model simply doesn't work. And that is called underfitting. Overfitting is the opposite case, when you have too complex of a model but too simple of a pattern. And what can happen then is they can find patterns that are not there, so it cannot accurately work. So it looks for the noise in the data will become patterns for the models. So when it tries to detect something on new data where the noise isn't the same, it fails, and it can do as bad as underfitted model. So this is the care nearest neighbor. Care nearest neighbors is a simple algorithm that stores all available cases and classifies the new data or case based on a similarity measure. This is mostly used to classify a data point based on how its neighbors are classified. So if if you have a new point which is the yellow square, it might label it as a green triangle, as there are two very close green triangle close to it, rather than a red star. So this is based on purely on how the training data look like to then predict new points. In this case, care nearest neighbors did not perform better than just guessing, as it detected very few events and mostly guessed 0 all the time. So it did not function at all in this case. This is the decision tree. This can be considered a nested if test in a tree-like shape. So it looks at some of the features, say if the elevation is higher than a number. If it is higher than a number, it goes to true and it moves to the one green circle, and then another feature would or the same feature would check if that is smaller than or bigger than a number, and then determine it from there. So these can be very complex, but this is a very simple and is a very white box of a model, as a lot of machine learning models are black box, as you doesn't understand how they function at all. They are not very intuitive to visualize, but this is a very visual model that you can show what is occurring in this case. This performed well with a recall score of 0.63 and a precision of 0.55, which is a fairly good model. Random forest is very similar to decision tree. This is an ensemble method, and it uses multiple full-size decision trees together, and from that it does a majority voting based on what the opinions of all those trees think of the data, and from that it does a majority weighting on whether it is an event or a non-event. So you can consider that many decision trees make a full random forest. So, and this is the reason why we do this is more resistant to overfitting. In this case, it performed barely better than random guessing. So if we just had a model would just guess randomly all the time, it would perform about as good as this model, unfortunately. So it's not a very, so the model didn't learn any particular patterns that would give it an advantage in this case. The final supervised method that we used is the ADA boost. This is also known as adapting boosting, and is also like the previous method, an ensemble method of decision trees. This uses a collection of weak learners that don't overfit at all to form a model. So uses very many simple methods together, and you get a results from that. So we uses what we call decision trees with only one node and two leaves, where the leaves are the results, so either an event or non-event, and this we will call as stumps. The decision trees used are much simpler compared to the random forest in this case. Here it performed nearly the same as decision tree with a recall of 0.62, but it has a better precision score of 0.65 in this case. We also took a look at unsupervised learning. We took a look at the care nearest neighbor outlier detection and isolated nearest neighbor ensemble. Care nearest neighbor is an outlier detection that looks for something that looks out of the ordinary in the data. So if you have a lot of green points in the data sets, as in the figure there, and you have a data point that is very far in like distance wise in compared to the other points, you would consider that to be an outlier and then detect that as an event. This doesn't require labeling in theory, which makes the scintillation file that was needed to label all the data not required, which is in some cases you don't have labeled data, so that is like the main difference between supervised and unsupervised. The unsupervised doesn't have the labeling at all, and this can be advantageous in many situations, as if you don't need the labeled data, you might not need an expensive hardware in this case. So, but in this case, we run up against saturation of data, as it was very slow at the full data set load that the supervised learning handled nicely. The initial result was not better than guesswork, but we think further work is needed as it was not fully explored in this case. So at the end, we would like to summarize. We have analyzed about 9 months of data from the Kiruna station in Sweden. We looked at multiple observables and selected from there several features after performing a feature analysis on the dataset. We analyzed multiple supervised algorithms, and the ADA boost and decision tree performed the best in this case, which might suggest that a simpler method could do very well compared to a more complex one. Unsupervised learning needs further development in this case, which is the further work we would like to see done is that we would like to see further development of the supervised learning method, and semi-supervised could be a nice compromise between the two, where it only needs some labeled data. We would like to parameter tune our models, as this was not as we could not do it at the current hardware that we had available. We had the larger data set to account for seasonal change, as we can see some hints that this might be the case. We saw a feature combination test that we performed to see which features are more important to the data set, to the models, than others. And we would like to further test our models more thoroughly, as this we think with more investigation might show some more potential. Thank you for your time, and if you have any questions, feel free to send me a mail at bethany@estecorp.no.